Do you have any questions about quizzes and lecture last time? Okay, so today we want to finish chapter 2, and after that we will have some exercises, and I'm planning to use breakout rooms. And after that, I take a survey on whether you prefer more exercises or more explanation in lecture or more materials covered in lecture. So last year, basically I have less exercises. One reason is that we have online class, and 2 years ago I have more exercises but slightly less materials covered. So I wonder which is better. Okay, so we go to chapter 2. We continue chapter 2, and we also do some coding demonstration for chapter 2 or our language in general. Yeah, okay. So last time that we started to talk about classification. So classification, in classification problem, that we are given predictors and also we are given the response variable that is a categorical. And the simplest one is binary classification problem. So we have two groups. So here that we have the orange circles and the purple circles, and we want to see that what's the best boundary. So we can do logistic regression for binary classification. What is the shape for the boundary if we use logistic regression to make to separate two groups? You know any? If you use the logistic regression, there we regress y on x1 and x2. What's the boundary by logistic regression to separate two groups? Say we make 0.5 as the threshold, probability of 0.5 as the threshold, then what's the boundary by logistic regression? I think that I assume that most of you have taken 50-30, so Antarang, do you remember what's, yeah. Oh.
Is it just a line?
Yes, yeah, it's line.
Yeah.
That's great. Yeah, so the logistic regression, we have a straight line. So basically, we are thinking about the signed distance onto some optimal straight line. So this observation have this distance, this distance, and this observation has this distance, and this observation has this distance, and so on. And based on this distance, we assign probability. So this is the threshold by logistic regression. Threshold of P of y is equal to 1 given x by logistic regression. But sometimes we want to have more complicated boundary. So in this case, we have the dotted line. So this is the more complicated boundary, and we will study another method for classification. So this is a non-parametric method called the k nearest neighbors. And k nearest neighbors, basically we pick up k nearest points to decide, which category that point belongs to. So you can see that, for example, in this figure, just pick up an arbitrary point maybe around here. Okay, then we pick up, for example, maybe 7 nearest points. Then that is 1, 2, 3, 4, 5, 6, 7. And out of 7, that we have the orange circles and the 2 purple circles. So it's more likely that this belongs to the area of the orange circles. So that is the idea of k-nearest neighborhoods, k-nearest neighbors. So if we use formula, that becomes this. So here, the x can be multivariate. So maybe in the previous figure, the pair of x1 and x2. So if x is given, so x naught is also a vector. So when x is given, then what is the probability of y is equal to j? So in the previous example, j is either 0 or 1 because we have a binary classification problem, but in general, we may have more than 2 classes. Then we pick up k nearest points and we calculate the number of observations which belongs to the jth class. So if we have 10 observations and 5 of them belongs to class 1, 3 of them belongs to class 2, and 2 of them belongs to class 3, then class 1, 50% probability, the class 2, the 30%, and class 3, 20% probability. So that is the way to define this probability in k-nearest neighbors. So here it explains. So this case, the k is equal to 3 on the left-hand side. So out of 3, the 2 blue circles and 1 orange circle. So that means the probability that the y value of this point belongs to y value of this point is purple is 2/3 and the orange is 1/3. And if we decide the probability in this way for each possible point, I think we have infinitely many points, but if we do that, then we can see this area, the more likely to be purple, and this area more likely to be orange. So we have to pick k. So here k is equal to 3, and you have to decide k. And k is generally chosen by cross-validation, which is covered in chapter 5 or 6. Yep. And the different k makes different boundary. So here is an example. So the purple one is the true line, so true boundary. So this is based on simulation, so we know the true boundary. Usual problem, we don't know the true boundary. So this is the true boundary, and this is the result by the 10 nearest neighborhood. K nearest neighborhood with k nearest neighbors with k is equal to 10. So for each point, we pick the 10 closest observations and decide whether this point belongs to orange or purple. And here is k is 10. It looks pretty good, and this black line is the estimated by nearest neighbor with k is equal to 10. And it is very close to purple line, so it worked well. And here, the same thing, but the k is equal to 1 and the k is equal to 100. So only one observation determines the area. For example, let's think about here. So there is just one purple circle that is a kind of an outlier, maybe more severe cases here. So one purple observation here, and this is a kind of outlier, but since the neighborhood of this point, the nearest point is purple, so this area is classified as purple. So it the boundary becomes unnecessarily complicated, it looks. And actually, if we compare the truth and estimated boundary, actually that we have larger error. And the right-hand side is k nearest neighbors with k is equal to 100. So I don't know how many points here, but maybe 200 points it looks. And so we take 100 observations. So when we move a little bit, still the 100 nearest points have a similar tendency. Maybe if we move from here to here, maybe the proportion of orange and purple change, but only slightly. So from here, maybe 70 of the 100, the nearest points are orange. And if we move a little bit, still maybe we have 65 or something. So the generally boundary is simpler. And you can see this black line is in some sense simpler than the purple line. Almost, black line is the straight line. Right? So in this case, it looks k is equal to 10 is optimal. So in general, some moderate value of k is the best. And this shows the what value of k is values of k is the best. And you can see the blue one is the training error. And this is the test error. So training error means that training error means that we choose just the observation, actual observation as the point of evaluation, and from each point that we apply the k-nearest neighborhood, and we see how many of them have more than 50% probability. So suppose that suppose that we pick up this point, right? So this point is the purple, and we think about just the 10 nearest neighbors. Then you can see that 9 orange points and 1 purple point. So that means the orange probability is 90%, but actually this is purple. So that means we have an error. And we evaluate at each training point. So that is then we can calculate training error, and that is here. And the horizontal axis is 1 over k. So that means so here I think the height is 1 over 100. So 1 nearest neighbor. So 1 nearest neighbor is always correct for training set, because we pick up just training data point, and we determine the 1 nearest neighbor. So that is that point itself. So always it's correct. So the error is 0. But the k is equal to 1 over k is equal to 0.1. So that is the k is equal to I don't know, maybe 5 in this case. No, 1. Sorry, the k is the k is equal to 10. Then 1 over k is 0.1. So in this case, that we have a slightly larger error, and the 0.01, that means the k is equal to 100. Then we have even larger error. And the training error that generally goes down as k gets smaller. But we have some fluctuation because this is real data and the data looks strange sometimes. So, but as a tendency, it decreases, the monotone decreasing function. And the orange one is the test error. So after we decided the boundary, we have a similar data set which is generated by the same algorithm, but it has some randomness. Then we see how many of them are classified correctly. Then if k is very large, the actually test error and training errors are similar, then it gets smaller, but not as small as the training error. So usually training error is smaller than test error because the training error uses its answers itself. But if the k is too small, so k is too small, then test error gets larger because of the kind of overfitting. You can see that if k is very small, then the boundary becomes unnecessarily complicated, and it's not close to the true boundary. So that means the test error gets larger. So we have some optimal point, probably I don't know, around here or here. So around here is the optimal point. So k is maybe 10 to 20, 10 to 15 is the best to choose. So in this way, this is non-parametric method, but we can have a better boundary. Yeah, so to summarize, the small k, we can say it's small bias and the large variance. So small k means that we can adjust to the data set very well. So bias is small, but the just a slight difference in data set makes boundary different. So it's not stable. So it has a larger variance, and larger k, the larger bias, and a small variance. This is classification, so it's a little bit harder to see what is bias and what is variance, but we can see this is for probability. Then this is the same as the almost the same as the regression problem, and the for probability of y is maybe y is equal to j given x. So that is, if we use a small k, we have a small bias but the larger variance. Do you have any questions? So this algorithm is pretty simple. Just you can find the k nearest points, then decide what's the empirical probability to define the probability of y is equal to j given x. Okay, so this is chapter 2, and I think there is one question asking the implementation of k nearest neighbors. So that is today's quiz. Any questions? So nearest neighbor, sometimes we say, usually we say k nearest neighbor, so k and n. So nn usually is reserved for neural network. So yeah, so maybe if we use k and n, usually people think this is the k nearest neighbor. So we have so many, abbreviation. So sometimes it's confusing. For example, CNN is usually the news network, but in machine learning world, the CNN stands for convolutional neural network. It's a kind of the slow learning, the slow version of neural network. So we summarize the information only slightly in each step. That is the convolutional network, neural network. So you can see that the usual decision making, usually we compress information, we summarize information a little by little, right? So if doctors see many images, maybe they at first maybe cut out the redundant the blank spaces. Then after that, maybe they adjust the angle of the image. Then after that, they just remove the redundant information and so on. So it's a pretty intuitive idea to summarize information slowly. So that is so-called convolutional network. But anyway, yeah, so this is chapter 2. Okay, so now the chapter 2 lab, I use a computer to demonstrate this. Okay. So oh, sorry. Okay, so this is the R console. And I would like to introduce several R code. And the chapter 2 lab is not directly related to chapter 2 contents, but it introduces some functions which are not introduced in Stat 5030. And also some of you haven't used R before, maybe 2 of you. So I just want to demonstrate some code. Okay, so our objective, you can see the chapter 2 lab slide. Our objective is to make a contour plot or a heat map, like the actual geographic map. So, okay, so at first we think about some very simple function such as x squared plus y squared. So that value is 0 if xy is 0, and if the distance from the center gets larger, then value gets larger. So it's a it's a parabola. So we want to make the contour plot of that and also heat map for that. Okay, so just we define x as a sequence of 1 to 10. We can assign the 1 to 10. So this makes the sequence of 10 numbers as a vector. And also we define y as 1 to 10. So y is also 1 to 10. Okay. Then to define the x squared plus y squared, we can make a function. We can name the function as f and the function of the xy. So this is x squared plus y squared. Sorry, it's a little bit confusing. So these x and y are reserved for, maybe just we erase this, and a capital X 1 to 10 and y as 1 to 10. Okay, then we define function f. So x and y are just variables, and we define the f as the function x squared plus y squared. So for example, f of 1, 2 is 1 squared plus 2 squared, so it's 5. Yeah, and maybe we define another a little more complicated function, the function xy, that is the cosine of y divided by 1 plus x squared. So this is a little more complicated function. And now that we want to make a contour plot and the heat map. So at first, we plug in all numbers 1 to 10 to 1 to 10. So any combination of the 1 to 10 and 1 to 10. And for that purpose, the one convenient way is to use outer function, outer product. So x and y, f. So we try all combinations, sorry, capital X, capital Y. So fxy is this 10 by 10 matrix. So for example, if we see x is 1, y is 2, then this is 5 because 1 squared plus 2 squared is 5. So if we make this object fxy, so this is just a matrix, output as a matrix, then contour of xy, fxy, then we can make, the x and y, then we can make, this figure. So you can see that at 0, 0, actually 0, 0 is not visible here, but around here, 0, 0, the value is 0, and this is the contour at 20. So you can see that if x is equal to maybe 4 and y is equal to 1.4, right? Then sorry, 1. So x is equal, y is equal to 2. Sorry, x is equal to x is equal to 2 and y is equal to 4. 2 squared plus 4 squared is 20. So that is the on this the curve of 20. And 40 and the same thing. So if x is, for example, 0 and y is square root of 40, that is about 6.3 or something, then it's on this line. So you can see. And I think this contour function have several options that we can make in this way. So also we can do the contour plot of gxy. Sorry, the gxy, we haven't defined it. Gxy is the outer function of x, y, and g. So gxy is this matrix. Sorry, it's so large. And the contour of gxy, you can make this one as this. But you can see that the contour plot of this complicated function, cosine y over 1 plus x squared, the curve is not smooth enough. So if you want to have more lines, then you can specify number of levels, 20. Yep. Then you can see more lines. Still, it's not smooth enough, and I don't know how to control the smoothness of this one. Maybe if we try more points, then it becomes smoother. But the contour plot have some options. You can see the help of contour to see what options are available. You can see the number of levels and the range for x, range for y, and I think the smoothness we can control in some way. Yeah, I cannot really see, but there are several options to change the graph. And also the image function that do the same job, but it creates the heat map. So it looks like real map. You can do this. So this is, yeah. So the resolution is not very high here, and I think we have some options to control it. But as x and y gets larger, the value of x squared plus y squared gets larger. And some other, the fancy graph, such as 3D graph, we have x, y, and the value of x, y. So it's best if we use the 3D plot. I mean, the 3D plot projected on the two-dimensional space, right? Anyway, usually we say that this is 2D if your monitor is not 3D, but yeah, you can see that this is x and this is y and this is fxy. So I think that we have options to change the angle, but you can see this is a part of the parabola. X and y gets larger, then the value of f of xy gets larger. Yeah, any questions? Yeah, so I don't really know the details, such as how to make this lattice the more, narrower, or how to change the x value, y value. Yeah, certainly we can change the range of x value and y value. Actually, we have x is equal to 1 to 10, but if we have -10 to -10, then f of, sorry, maybe probably it looks different, right? Like this. And also, I think that there is a version, the dynamic version of this, so that you can interactively change the angle. Okay, so anyway, so this is not really the main part, but I would like to explain how function works. I would review how functions in our work, and also some graphical implementation. Okay, so now that we do some data analysis, the ISLR is the name of the textbook, Introduction to Statistical Learning with R. And the library ISLR is the library developed by the author of this textbook, and it includes the several data sets. So, for example, that we have the auto dataset. Auto dataset has the data for 392 different car models, and the variables are mpg, mile per gallon, and the number of cylinders, and the displacement, and horsepower, weight, acceleration, the year, and the origin. Origin is either Europe, United States, or Japan, and the name of the car. So you can see first several ones like this. So these are all American cars. So origin is, I think, 1 if it's made in the United States, and the year 1970. So it's very old car data. Buick, Skylark, I don't know. Yeah, Malibu is still available in US market, but others I don't really see. AMC, I don't know. I know GMC, but okay. So then we have many ones. Yeah. So unbelievably inefficient cars. We have many cylinders, and the displacement, I'm not exactly sure about the unit, and horsepower generally low, and so on. Yeah. And there are some figures. For example, the number of cylinders, what's the distribution of the number of cylinders? We can use the plot function, certainly, to make, for example, the scatter plot of cylinders and the MPG. Oh, okay. So at first, these variables are within this data set. So to create a graph, we have to either specify the $sign. So this means the MPG within auto dataset. Then you can see this, the scatter plot. So cylinders and the MPG. So more cylinders, usually larger engines. So nowadays, it's really rare to see cars with 8 or more cylinders. But anyway, so these are very large engines. So you can see MPG, the fuel efficiency is lower for larger cars. But also here, it's not good. And another way is, attach the dataset first, then just use these local names to see this. But usually this is better explained by the box plot. So you can make it as a box plot. So there are several ways to make a box plot, the box plot function, but also as long as the cylinder is a factor vector, it automatically becomes box plot. So we define cylinders as a factor, a variable, then a plot of f dot cylinders and MPG. So this becomes this. So it's our box plot. So you can see that clearly the smaller number of cylinders, the better fuel efficiency. The name has been changed, and I don't know why. You can change the label. Y label as MPG, something like that. Yep. Yeah, there are several other functionality, such as a variable width is equal to true. Then you can see, oh, sorry, it does not work well. Variable width. Oh, I see. Variable width. Yeah, so now it represents there are only a few cars for 3 cylinders and 5 cylinders, most cars. So this width represents the number of observations. So the most cars have 4 cylinders. And you can also change the X and Y axis, exchange the X axis and Y axis by the specifying horizontal option. Then we can see the MPG is here. Oh, yeah, I think that should be opposite, but yeah, so MPG and cylinder just transposed. Yeah, and often the useful function is to see the data is the pairs function. So it makes the pairwise scatter plot. So MPG and also, for example, displacement and the horsepower, horsepower. Sorry, we have to connect with plus. Weight, acceleration, Yeah, then we can make this plot. So you can see that it's not really linear relationship, for example, between MPG and horsepower. And some are linear relationship, it looks linear, weight and horsepower, for example, because probably car makers design cars to be linear. Yeah. Another way is that you can use just the original data set and you specify some number of columns, the column numbers. Then we can make the same plot. Yeah, and sometimes it's useful to have the interactive functionality over this scatter plot. Okay, so suppose we have one scatter plot and the identify function and horsepower, MPG name. Identify horse. Oh, I see. Sorry. Horsepower MPG. I don't know why it does not work. Oh yeah, yeah. So if you click it, then you can see which observation is which. For example, this is a kind of outlier. So this is Datsun 280ZX. And this is Ford. Horsepower MPG, lower horsepower, lower MPG. Volkswagen Type 3, Mercury, and yeah, some dynamic functionality in our language. And maybe you can save it, then it may be more informative than just a scatter plot. Okay, so that's chapter 2 lab. And now I want to start some exercise. Exercise is available in Canvas, so you can now access to Canvas to see exercise. And I'm showing this exercise. just a starter. So the first question, it asks to define the functions, just a function, f of x, a function of x. Then calculate f of -1, 0, -5, and also create a vector and the value of the function for many values at once. Actually, if we put vector in this function, then we can get the all answers. And make a line graph, and we can find the largest root of f, and so on. And the question 2 asks to import the data set and then calculate something. So data set is also available in Canvas. And yeah, so I will make a breakout session to do that, but just download the exercise and the data set. And just to read the data set, just one thing I want to mention. So you have to set the correct working directly to import the data set. And I recommend to type the get WD, get working directly, then you can see the default working directly. Then after that, you can see the format of writing the path in your computer. So then you can specify the specific directly where you want to save your data set. Okay. Then you can import the data set from here with using the read table function. Read.table to import data. Okay, so maybe I will make a breakout session for maybe 5 minutes to make you discuss how to do it. I don't know how many participants. Maybe I will leave the session. Yeah. And how many? We have 12, so maybe we make maybe 4 rooms to make you discuss. Sorry, I'm not exactly sure. Breakout rooms, yeah, 1, 2, 3, 4. Okay, assign automatically. Yep. Yeah, especially if you haven't used R before. I think that most of your classmates have already used, so you can ask question and discuss it. After that, I will ask how to code. Okay, so maybe 4 to 5 minutes. Sine 2, 1. Okay, so okay, so have you done the questions? Yeah, I think there's so many questions in 5 minutes. So make a line graph. Does anyone or any group identified what is the largest root of f approximately? Not enough time? How about Shuraya?
I was still downloading my file, so Didn't get
Oh,
it.
okay, but the question one, I mean,
We didn't even work on that.
you didn't? Question one and question two. So question 1E. Not yet done. Anyone else? Anyone has identified what's the largest root of f? Yet. Maybe 5 more minutes. Okay.
Professor Weaver, we didn't even make it through part A of the problem.
One?
Just so you know.
Yeah, we didn't make it.
Okay. So
I had some issue with syntax and they were teaching me.
okay, sure. Anyone else got the answer for 1e, the largest root of f? Just approximately? Not yet? Like, I don't know. Okay, still, okay, so some are, the rooms are discussing. So how about room 1? Psi? Did you? Okay, so has any room identified the solution for 1e? Not yet?
Approximately like 4.2 or 3 or something.
Oh, right. You make a sketch up, maybe the line graph, maybe.
Yeah.
Okay, great. So any others? Maybe more accurate answer, such as, 4.35 or 4.25. Okay, so we start discussing that. Okay, so at first we have to define the function. So 1a. Define function f. The f should be the function of x, and x is x. The function is x cubed minus 5 times x squared plus 3 times x, or like this. So you can see, for example, f of -1 is -9. So you can see -1, -5, -3. So that should be -9, and f of 0 is 0. Okay, so that's almost obvious. And f of -5 is the -265. Maybe f of, you can see, for example, f of 0 to 5, f of f0, f1, f2, f3, f4, f5. Now you can see that we have a solution between -4 and 15. You can see the intermediate value theorem in calculus that we at least have 1 0 between x is equal to 4 and x is equal to 5. So yeah, and okay, so now that we want to calculate this value from -1.00, -0.99 to 5.00. So how to do that? We can make a sequence, but if we multiply sequence by 0.01, we can make this. So -100 to 500. Suppose this is maybe capital X, then the first 5 elements of capital X is here, and we have the 601 elements here. So for example, the last several elements, if you print out, then this becomes the 4.94 to 5.00. So we can define the y value as, okay, so f of this x. Okay, then you can see the first 6 values of y's are -9. This is f of -5, f of -4.99. Sorry, the f of -1 and f of -0.99, f of -0.98, and so on. Yeah. Okay. So now we make a line graph. So we have y and x, so we can make a plot. But if just we make a plot, this is almost okay. This is almost okay, but this is not a line graph, but just a scatter plot. So to make a line graph, type is equal to line, type is equal to L. Then this becomes a line graph. And we want to find a root. So maybe it's convenient to have y is equal to 0. So AB line, intercept and slope. So y is equal to 0 plus 0x. Namely, y is equal to 0. Okay. So AB line just overwrites this graph. So we have the 2 levels of function in R. So this is plot function. It reset the entire pane for the figure. And the AB line is just an add-on to the plot. So you can see this. So we have one root here, and another root here, and this is largest. And as the Antarang mentioned, this is maybe 4.2 or 4.3. So we want to narrow down. So we take the absolute value of this function, and we want to make the smallest one. So to make it, maybe we just pick up 4.01 to 5.05. So 4.01 to 5.05. So that is 0.01 times 1 to 100 and the plus 4. We redefine x as this. Maybe we define x2 as this. So x2 starts with 4.01. And we can make the f of x2, right? F of x2, but we take the absolute value of f of x2. I would say this is y2. And y2 is what? The y2, okay, so the first 6 observation is like this, and we wanna find the smallest value, right? So that is the rank of y2. Yeah, you can see that here it's smallest. So this is, okay, this is the 17th observation, and this is 33rd observation. So 1 is okay, so this is 33rd, 32nd, 31st, and this is 30th, right? So that means the 4.3. 4.3 is probably the closest to the true answer. Maybe we can try 4.3, maybe 4.29, 4.31. You can see the 4.30 is closest to 0 in absolute value. So this is approximately 4.3. So that is the answer. Okay, so now maybe you can do question 2. So maybe I will make the breaks out session for another 5 minutes, 5 to 6 minutes. Okay, so enjoy your session. Okay, so still 5 seconds. Okay, so I make a survey on your progress. Maybe one more. No, actually, that's me. Sorry. Yep. So yeah, I'm sorry that this is the first exercise, so you may have trouble to import the data. But just make sure that the you are able to import the data. But actually, maybe 8 of the students finished at least A. Okay, so I explain at least maybe the first few questions. And maybe before that, maybe, yeah, I will explain that. Yeah, sorry. Share the screen. Yeah, so I'm sharing the screen. So at first we have to import this the data ex.toCSV. So now that I set the directly correctly, so I can read the data set. Maybe I name this data set as my data and the read.table, and then you can type the name of the data set. So data.ex2csv. Then this is okay. So comma separated file because this is CSV. So the separation symbol is this, and it has a header. So header is equal to true. So you can see that my data is this format. We have name, gender, height, and weight. So this is totally fake data set. So just I picked up some first names on some random website, and I just created this data set. So I imported the data set and I calculate BMI for each. Sorry, I didn't have the definition of BMI, but the BMI is the weight divided by height square. And maybe before that, I have to attach this data set. The 2 line can be put in the same line if we use this separation symbol. So in this way, we can define the BMI. So BMI is height square. So yeah, so height is in meter. So I think that this should be height divided by 100 the square. So height maybe 0.01 times maybe height divided by 100 square. So usually we use this one. BMI. So head of BMI here. So the first person BMI is 24.8. So 24.38. Sorry. So this is 164 divided by 1.62 square. So yeah, in this way you can make a BMI. Then sort the data frame by decreasing order of height. So this is a little bit complicated. So this is C, right? So this is C and the decreasing order. So my data, and we change the order of rows. So row is the first index. So we have to do something in the first index. And the first index is the order of height and the decreasing. So usually it's increasing order. So decreasing is equal to true. Or after we order it, we just reverse the order. That is another way. But in this way, we can make it sorted by height. You can see the first person has the highest, is the highest, and second person, second highest, and the last person is the lowest. So we can see in this way. Yeah, so order function can be used to sort this data set. Okay, maybe I think that most people, none of you did the D or later, so maybe I will upload the answer. And at last, I would like to make another survey on what kind of lecture style is preferable. And either you want more exercises in the future, or individual exercises, or more explanation by me, or more contents to be covered.
I'm sorry, Professor. By more explanation, you mean like what you're doing right now, like explaining the exercises?
Sorry, it's not clear, but yeah, I think the more detailed explanation for chapter materials.
Okay.
Sorry.
So if we wanted you to do exercises like this in class, which one would we answer?
The first one, exercise in breakout room, but if the breakout room is annoying, then you can also answer individual exercises. Maybe one more person. I got, okay. So yeah, no tendency. So 6 people say more exercises and 5 people say the more explanation or more contents covered. So maybe I will have some exercises, but not too much exercises, probably. Maybe once a week for maybe 20 minutes or 25 minutes, maybe. Yeah. Okay, so today we only have one quiz question. I think it's available, or yeah, so one quiz and the due Monday. So yep, so it's the 6:48. So I finished the lecture, and the next time that we start chapter 3. Yep. Okay, so see you next week.
Thank you. Bye.
Thank you.
Thank you, Professor. Bye.
Have a nice weekend.
You too.